topics. The main content actually was presented in various places, including a seminar that I gave at the Max Planck Institute for Mathematics in the Sciences in Leipzig, where there are people also working on these topics. So on this topic of morphological computation, which will be more clear to you, I hope, at the end of this seminar. So for those of you who were here already on Wednesday, let's say that the point of view on robot is still about robotics, but the point of view is completely different, because in that case, we were focusing on available technology, consolidated scientific approach, and application and impact. So that was what we know that we have now, what reasonably we will have in 5 years, maybe 10 years, and how this can have impact and can be exploited in application. Today, the topic is rather different, because what we are focusing on is what is not working, and how we can develop methods to go beyond what can be done today. So while in this bunch of, while the other one was really much linked to what we are doing in Spark, which is a public-private partnership with European level, which is fostering what is called roadmap-based robotics research, which means research where you can write a roadmap. You can write a roadmap of research if you more or less think that the paradigms are known and the problems are known. Now I am using this affiliation, which is actually the fact that I'm leading this working group inside this Robocom++ project, which actually aiming to to outline the paradigm of next generation robotics. So some of you may have, well, next generation mean, but I will come on this because it's easier to explain a bit slower. About you may imagine what I'm going to say. So really in short, something that I may have already shown if you were here in one of the previous seminars. So the point is that if you look from a very high-level standpoint to robotics, you may observe that there were already robots. They have been for centuries, thousands of years. Basically not very useful until very recent times, when the microprocessor allowed to do more complex tasks. But you may also observe that the principles are the same. So if you look at those Renaissance automatons, and you look at these very modern androids, conceptually, you see the same kind of machine. Because in that case, you see a clock-like mechanism that in modern words is a program implemented on a state machine, a short program on a small state machine. And here you have, again, a mechanical structure driven by a very complex state machine. But basically, the idea is that I have a computer program running of what you can consider a von Neumann architecture, driving some motors and getting back some information. And this is something that I like. I may also skip, but not many people know that during the exploration of Far West, there really a lot of first half of 19th century, a lot of migrant expedition to the Far West went lost. So a lot of people died while trying to reach the West. So at some point, the U.S. Army decided to write to commission an handbook with the basics on how to reach the Far West. And what I really like is the introduction, because in the introduction it says something that is still true in science, and it is a caveat for what I'm going to say you today. Because the idea is that, of course, when you get information on how to reach the Far West or how to make research in robotics, you will get different suggestions. Even someone will tell you to go by sea, and someone will tell you to go by train to Chicago and to continue with carriages. Someone will suggest something else. And the suggestion is, well, consider all these suggestions with care, because all the people managing the different routes have vested interest. So they have already invested on that route. So for sure, a ship operator will suggest you to take a ship until to go to New Orleans and then continue on the other side. A train company will suggest you to take a train. So, and this is will be a bit clearer before. So substantially, there are also a lot of people who most of the community, including partially also my institution, are already involved heavily in what I have dismissed as the mechatronic paradigm. And who was here on Wednesdays knows that I don't downplaying the fact that that kind of approach can have now that we have powerful algorithms and powerful computers. However, there are some limitations, and I am starting today from those limitations. So actually, if you check the idea of robotics, this is a very widely cited phrase from Aristotle from Politics, where basically Aristotle was trying to justify the necessity of having slaves. Because the idea was you needed to have a few people thinking about strategies and doing research and discovery. If you wanted to free people from the everyday course, you need someone else to doing that. So it was very clear. And he said, so it's sad, but we need slaves. But already Aristotle, so I don't say that I agree with Aristotle, but this was his very rational approach to the problem of slavery in Greece. It's very interesting that he actually, this was the phrase before, what he said is that, of course, if the machine could govern themselves, we would not need slaves. And from my point of view, this tells everything about the potential impact of robotics and AI over society, because they are still forms of slavery, in the sense that we every day fight to leave to other people the boring stuff and the non-prestigious stuff. AI and robotics could help us to delegate to machines, and so we are happy and we have less conflict. What is interesting, I enter in the, is that from a pure conceptual analysis, if you check, as my colleague from Greek colleagues who actually had a PhD in Greek literature, ancient literature, if you check the original text, not the English translation that everybody quote, you see that Aristotle was already aware of the fact that if you read here, if you want to have a machine that really is able to interact with people, a real robot, you need to have a capacity of anticipate the perception. So this phenomenon before, so understanding in advance. So it was this piece of text, as it was initially brought in Greek, could have been in a research proposal in AI of nowadays. Of course, the problem of the poor Aristotle was we had no ways to do what he was analyzing. So, and again, insisting on the concept of a factor. So here you see, this is probably the oldest handbook of robotics ever written. And it is a Japanese manual about how to build this small automata. What you should focus on are these gears and pulleys, because if you have gears and pulleys and levers, you basically can implement some basic functions. So this approach has been very very successful. But as I put in the subtitle, it shows some limitation. So let's discuss this point. So I was a bit unfair because I'm showing only the bad examples. So actually, many times, the robots are able to open the door. What for me is more striking than and this is something that if you check in YouTube with on the Asimov falling from the stairs, you will see, again, a very funny situation where since it put the foot in the wrong place by less than 2 centimeters, it falls down miserably. Now, because the approach, whatever you think is a very long program, hundreds of thousands, if not millions of lines of codes, governing a big clock, because this is the human. If you want to have an idea in terms of cost, we are talking of machines when they cost they are cheap, they cost $500,000. When they are expensive, they cost 2-3 million. So they raise humanoids in the challenge were above 2 million. But what for me is more surprising, the number of people that were teleoperating the robot. So you have hundreds of thousands, sometimes millions of lines of code. 10 people or more teleoperating the robot, and you get this. So you have problem in opening a door without falling. Also humans sometimes have problems, but in this case, it's more up. So the idea here is that, and here is the caveat, so that many people in the community, for example, my institution, but also PFL, a number of institutions around the world are in Harvard, VC Institute. So there are a number of groups, these people in Max Planck, who thinks that maybe we have a paradigm problem. So we should go beyond building a big clock, so exploiting the possibility of writing huge programs on a computer and trying something different. Because the problem here is that what we are doing with these humanoid robots, we try ever and ever to do more complex things. And the humanoids are example of machines trying to do, drones or mobile ground robots or self-driving car are somehow simpler, performing simpler tasks than a humanoid. Humanoids are machines that are developed mainly for curiosity, so to see what can be done. And what we have discovered that we have a lot of problems. Of course, the caveat, maybe we need more computing power, we need more components. The problem that is underlined here, what is underlined here is that what happens is that as you add flexibility in the behaviors and you complexify the behaviors, you have an increase in complexity of a code, because finally in a robot you have a long set of programs interacting with each other, and you have more components. So you need to add more components. So we don't, there is, for example, if you are interested, I can show you, there is a very nice discussion in a book by Daniel Dennett, the cognitive philosopher from the US, who analyzed the problem of a robot taking a bomb out of a room. And it shows clearly that if you want to manage the unexpected situation, you do what we basically do in the robotics community. So you add more and more new routine to manage more and more exceptions that you discover while using the robot. And this is, the idea is that if you look to nature, it seems that we have a lot of examples of working robots. So if I look at an ant works. An ant colony is 10 of thousands of small robots interacting effectively. So the idea is, okay, it seems that we have facing almost impossible challenges in developing robots. But if you look around us, there are a lot. So the origin of this, which is a running project on this new approach is, but may we look into nature and to see how biological systems do what we want to do with robots. This is, and this is the purpose. So what in nature we see a number of things. Another thing that it is happening that justify this interest for so the idea is, okay, I have, this is what could be controversial, because I say, okay, I have used all my arrows, so I am using fast motor, a lot of computing power, and the results are those that I have seen before. Maybe I'm not trying to solve the problem in the right way. Let's try another approach. And so, really, I look at intelligent natural agents, and I try to reverse engineer the principle that evolution have developed so far. And this is one reason. The other reason is that during the latest years, what is happening is that especially people working in prosthetics have more and more interaction with people working, for example, in medicine. So, because if I want to build an hand, and the hands that you find now are hands like those of humanoids, so electric motors. I needed to wire my robot hand to something that, by the way, has been done already a few times. I need to wire to the arm, because the people need to be able to send the command to close the hand and need to, for example, be able to have a sense of touch. You should amputee your hand and put a prosthesis to understand what the amputee to whom you have connected a prosthetics and really feel. But they can feel, for example, if it is rough or if it is not rough. My personal idea is that they don't feel the same that we feel, because we don't connect enough wires. But they feel something. So this leads the people here in robotics to try to understand what's the code of communication. This code of communication is strange. Because, for example, the nerves, for example, I was naive. Until a few years ago, I was absolutely naive on these topics. You may think that the problem is that the nerves are very small. No, they are in the order of 1/10 of millimeters. So they mix that with a microscope, and with a proper tool, you can actually take a wire and connect. What the challenge here is to understand what is going up and down in the nerves. So there are people working on this. And there was such a huge advancement on this that we are already talking of high bandwidth brain-computer interface. I don't know what, the problem when research is performed by a company is that you know very little about what they are doing. But the point is that they are working, Neuralink for sure, but also this researcher, which has another company, because we understand also the business potential of being able to connect a camera to someone who has not eyes, or X-rays to someone who has normal eyes. So there are a number of nice applications for this thing. And to tell you that we are really talking about something real, DARPA, which has a tradition of setting very high challenges. So to put the objective a little bit beyond what we know we can do. In any case, in March 2018, launched a call for application for high bandwidth neural direct interface. Because, of course, they are always dreaming of a super soldier, the robots are not good, but you may have some vision system which allows to see behind the walls, for example. So there are a number of interesting applications. But, okay, so increasingly, so there are issues and there are attempts to find a solution to these issues. So if now we are here, so there are two issues, because one is that when you look at those results in the challenge, you have some doubt that maybe we are not, so because you read the papers or you see the videos on the web, and you think that we have already robots. No? I think to the Boston Dynamics robot opening the door and working in the wood. No? So, okay, so it's done. Well, it's not so clear, because then when you challenge the community to say, okay, send your robot and open this door, it happens what you have seen before. I would say Boston Dynamics is probably one of the best, but videos are really not particularly indicative about the real state of the art. So increasingly we see robotics. This is the idea behind this new 1-year-old journal, so comparatively new, is that robotics has also a scientific side. This scientific side is to understand how intelligent behaviors can emerge from a physical system. And this is the same. If you want to build an artificial system to do something, for example, nanorobots for killing tumors, or if you want to engineer lymphocytes to do the same job. So the underlying logic should be the same and should be known. So a problem that if you pretend to be a science pops out immediately is the methodology. I will go fast on this because I think you will be more interested in the model impact. But in short, what happens in the robotics community is that there being a long discussion started some 10 years ago, because usually you cannot reproduce results. And this, if you aim to be considered a scientist, is a big problem. So because the cornerstone of a scientific method is you do something. For example, my robot is able to cross this room without falling and going out. And I should be able, following your instructions, in my room, in my corridor, to do the same things and obtain similar results. Not the same, because all rooms are a bit different, but I should be able. This is, most of the cases, not possible. Only very recently, we have at least, we have actually at the moment just one journal where you can submit reproducible robotics. As you know, it's a general problem because the publisher-perish culture is creating a lot of problems. For example, you know that they did a survey of, they tried to reproduce a significant sample of a paper in psychology, and only 1/3 were reproduced. So what means that most of the things that you read on the magazine about what you should do to live better are based on science which is not so stable. But in that case, is that the pressure to publish may have pushed a lot of people to publish results that were not real results. But in the case of robotics, that we don't exactly know what we should reproduce. This is the state. So to make a very long story short, we know from the high school what's an experiment in physics. We know that this concept has evolved to build machines like this Large Hadron Collider. In the case of robotics, it's a bit more complicated because it's not a robot is not as complicated, as complex as a living being yet, but is similar because you have many levels. Because in the pendulum, you have a simple law, and you can build a simple experiment. In the Large Hadron Collider, you have, again, simple law. You know how two beams of protons can collide, and you know how to calculate the different collision path. And so it's still the kind of experiment that you see in the pendulum. This is more similar to what they do in biology, because if someone falls down, can be because he put the feet in the wrong place, but because he had a problem in the brain. So or because he has a mobility problem that he didn't notice before. So this is true for people, and it's true for robots. Robots are still simple compared to the animal counterparts. But we are getting closer. And in fact, one of the sources of inspiration is the methodology. So I really don't want to spend too much time on this, but there are also very mundane housekeeping, if you want, issues related to the possibility, to the fact that we are not so good at comparing results. Because these are two examples. This is a bio-inspired robot, the Roomba, and that is the Dyson robot with SLAM. This costs 3 times as much as this. Should I buy this, which costs less, or should I buy the other one? It's not, for example, something that I can't use without doing an experiment. This works also if a room is dark. No? But this kind of comparisons, so I can kill the Dyson vacuum cleaner by switching off the light. But we are still starting to do this kind of comparison. So a new kind of papers have been introduced where basically departing from the tradition in robotics, people need to do what from school you would think you always have to do. So to define the assumptions, say what are your criteria to say that something is good or not. For example, if cleaning in the dark is a criteria, the Roomba is better. If cleaning in less time, the Dyson is better. So, I mean, you need to say, when you, so to structure a bit then point 2 and 3, you see this is, so because in essence to make a reproducible robotics paper, you need to give a description with hypothesis criteria and share the data sets, share the code, and tell me at least if it is not an open source hardware, tell me which hardware you used in your experiment. So point 1, point 2, and 3, point 4. And so on this, I really go fast. So you can check RAM, particular this article where all this is discussed. So what I should do, and a big question is, should I follow this approach, which is the traditional, and when I mean traditional, I mean from the ages. So build a state machine using my computers and connect to sensors and actuators in a deterministic way. Might be using some filtering of the data, but basically a deterministic machine. Or I should look deep in what nature is doing, where basically here I have a top-down control of a deterministic system. Here I have emergent information processing, intelligent behavior from a huge number of loosely connected parts. Because what is striking from the engineer looking in the cell is that you don't find a real center. Everything self-coordinate, self-organized. Life itself is a form of self-organization of complex chemical molecules. So at this point, the question is, can I copy? And the reason why I am so interested in comparison is that it becomes, if you go back, is an issue like, should I take a ship or should I take a train to Chicago before going with my horse to California? So it's a typical example of paradigm clash. So some people think that we should go in this on the right side, and it is difficult because we don't have many ideas about what I want to share with you as some ideas on how to go in that direction. Or should I stay here and limit my expectation or waiting for more computing power? And these are the two visions of intelligence. No? So should I think of AI, so artificial and natural intelligence, as a basic form of computation, or I should see it as a set of emergent self-coordinated processes from sensory motor coordination? Because if you look at the development of a baby, the baby co-develop the actuator and the behaviors to manage the actuators. Because now I can grasp this, but it took a lot of time because many years ago I don't have memories about that. But we know that baby start with an arm which is much less good of this, try to reach two objects. And while they do that, they develop the coordinating structure in their brain. And so this is really a long story, but the baby itself, it's a human baby. So it comes after several billions of spontaneous evolution of the plant. So before the baby, there was a monkey baby, and before there was an eukaryote, and before there was a bacteria, and before there was, we don't know, a collection of the RNA pieces sometimes reproducing, not all the time. So this it's a very exciting program, but it's really a basic science program because we needed to open the Pandora. And so this one is this, computation of emergence. And think that there are waves of fashion in these things because, for example, in Europe, this approach has been the absolute common sense for about 10 years. Then it didn't lead to significant results. So it was clear that people humbly working on mobile robots or drones obtained something more, at least economically more interesting. And this is now, again, not the mainstream. That's why, so it's, but the reason is that where these people failed, it was to find models. Because in the end, if you ask me, I'm a trained robotics engineer. So if you ask me to design or to organize the design of a humanoid robots like those of the DARPA challenge, I know from which shelves I should take the books and the equations. So I know where I have to copy. If you ask me to build the same kind of robot inspired by these principles, and there are good reasons to do that, I don't know how to do. And again, other example of more simple, detailed paradigm clash. People use the word soft robotics with two different meanings. Because some people mean, like for example, at TLR or KUKA in one of their products, they mean I have a rigid structure, so a serial kinematic chain, in this case, two serial kinematic chain connected to a torso, that I can model with a rigid body dynamics with little problems. And I say that it is soft because I add some spring, so some compliance, and some damping. And this is an approach to soft robotics, where people feel, again, more confident, because, again, I take the equation of the mechanics of a rigid body, and I add some complication, but still, so, you know, the basic Hooke law, I add the Hooke law, the equations are more complicated, but still is deterministic modeling of a structure that I know. Here, other people, for example, some colleague of mine in Pisa thinks that, no, well, this is not soft robotics, not what I really mean when I mean soft robotics. Soft, I mean soft. So completely deformable structure with distributed sensing and actuator. Why it is a clash, very similar to, because this, everybody knows how you can do. This, we are hic sunt leones. No? And now we are going to see some approach that can be used in this area. So, sorry for this maybe long introduction, but I think that it is important to understand that walking, for example. Well, a robot walking, a humanoid robot walking consumes 20 times the quantity of energy consumed by a typical human. Because in the case of humanoid, standard technology humanoid, everything is actuated. So the humanoid calculates the center of mass, extrapolated the dynamics, and then put the feet, wait a minute to see if the calculation was correct, and then put down the feet. This consumes a lot of energy. And also a lot of code, because you needed to do a lot of calculation. What happens, I will show you a video towards a bit later. What happens to humans is that you basically move the arm in this way without doing any calculation, and then you let it fall. When it falls, the energy that you consume is not used to move, is used to recover a correct posture. But in a very, so the result is that you don't use energy to move the leg forward. The energy comes from the gravity. And this is a typical example of what we call, someone had developed some biped walker on the basis of this, it's called passive walker. And what is striking is that for this humanoid, you have to manage the walk, you have 10 of thousands of line of code. There, you just have a small push to the drive here in the hip when you touch the floor. So it's not only consume 20 times less energy, also has very short programs, so they don't process information. So the information is processed by the dynamics of the body. Then if you add exposure to control theory in practical settings, the strange thing here is that when you develop a control system for application, you try to avoid limit cycles. So dynamics behaviors where your system will end up and will continue to periodically or with some strange period, chaotic periodic behavior will remain stuck. Actually, in nature, limit cycles that engineers traditionally avoid are the basis of the behaviors. So we work using the limit cycles. And this is a rather unusual approach. But then so nice. But if I want to exploit, because now the challenge is, OK, you are able to build 2 legs using an inverted pendulum model to work down a slope. With a small motor and a small program just giving an impulse every time that you detect that they have touched the floor, you are able to work. But are you able to build a humanoid like that of the DARPA challenge? Because if you are able, maybe next few years you will win the DARPA challenge. I'm not able. I'm not able because I don't know how. I'm not yet able. I'm not yet able because I don't know how to quantify this trade-off between the length of a program and the part of the behavior which is managed by the physics. So the morphological computation problem is to develop models which allow to predict this trade-off in order to have the tools to design another robot. So the problem is how I can develop a system. No? And I want to develop, so the main point, I already told you this. No? So the point is, so I want to develop a framework where intelligent behaviors, and I don't have huge expectation, at least walking, and the possibility to change speed when the system works, emerge from the sensory motor interaction. So is not pre-programmed. From what? From parts which are loosely coupled, and where I exploit the fact that they are physically somewhere. You will get, so, and if you wanted to split a bit more, is how in a physical agent, so in a physical system, the information and the physical behaviors are related to each other. What happens when I have more bodies? Because in a cell, I don't have a single body. I have many molecules interacting in a way that seems absolutely chaotic. And it is formally chaotic, but the emergent behavior is a super organized, super fit, and adaptive behavior. And maybe point 3, that could be more, how intelligent behaviors can emerge from it, because a cell metabolism actually is a form of, a cell is like a factory. So, but the difference with a human designed factory is that in the human designed factory, we decide top-down what to do. In the case of a cell, this factory has emerged randomly, and it still works on those principles. So, different approaches. In particular, one approach is this approach, which is called as information-driven self-organization. Information-driven self-organization means, and there are examples in simulations, small, nice simulations, by these guys, Prokopenko, Dalsbrev, who now retired, was actually one of the people, I think, that did more on this. They have shown that you can have this kind of emergent behaviors. For example, one example that for me is super impressive is this example of a snake bot. What is the snake bot by Ivan Tanev? That is now, I think, in Kyoto University. So this seems Crotalus, no? So a simple kind of snake. what is this snake from the mathematical standpoint? It is a series of balls loosely connected, where loosely means that there is a small probability function connecting the center of this ball to the center of the following ball. And, okay, nice. So it's a really a kind of model of this loosely coupled example. The other thing is that how it is programmed. It is programmed in this way. The controller, which in this case was a neural network, but could be everything, maximize the predictive information on the next position of the actuators, because the system is actuated initially in a random way. Then the weights of, in this case, the weights of a neural network, the parameter of a learning system, are adapted when because the point is that I send a message to the actuator, a signal to the actuator, and I see where the actuator ends. By calculating the predictive information on the difference, so in short, the mutual information between the real position of the actuator and the expected position of it optimization. So by optimizing this parameter, what happens is that this snake behaves like a snake with a difference with respect to other approaches. That when I change the floor, it adapts to the new floor. So if I start with talking about benchmark, if you benchmark this snake with a snake robot built with deterministically collected parts, on this flat floor, the other one behaves better. But if I change continuously the form of the floor, and this is a very simple approximation of what happens in the real world. So the real world changes all the time. This kind of approaches show extremely more efficient. So the idea of this is that this mechanism, so the maximization of some matrix of information related to the mutual information between the expected value measured by the sensors and the real one can be what drives the organization of behavior. Because when I say self-organization, okay, self-organization, what does it mean? So I need some criteria to drive this process, no? Because we are not, because I think one of the, sometimes people were a bit doubtful about that, is that, okay, self-organization magic seems magic. So if you don't want to talk about magic, you need basically to write an optimization function. And then the point is, okay, but what I optimize? For example, the idea of an information-driven self-organization, you optimize this. Because, in fact, so why you have so morphological computation is so ubiquitous in nature? Because it seems natural that for an animal consuming less energy to perform the same task will have more probabilities to survive. And a short program, a short control program, we will have more probability to be sorted out by a random process than a long program. So from a point of view of nature, it's quite natural to exploit morphological computation, so the dynamics, because having a long program working correctly is less like if you obtain the program by chance, no, by sampling. It's more difficult than having a much shorter one. So the control program in nature of movement are short. And it's, from the evolutionary standpoint, it makes sense. So still in this approach, no? I dramatically tend to go too long. But the idea is that traditionally AI has been considered, traditionally, not only traditionally, because has been considered a mind problem. No? So typically you think of AI intelligence as something that you put in a program in your computer. Even Go, winning a Go, which is very interesting, but Go is still a perfect information game. So you know, you know everything about the Go gaming arena, while you don't know everything about this room. You don't know where is a meteorite coming here, or so it's clear. So it's still a perfect information game. It's as much more possible moves than chess, but it's still something that you play in an ideal world. In nature, the only intelligent system that we know, including us, are embodied, so are physical systems. And you also understand why roboticists like this approach to AI, because it means that a real AI will be embedded in a robot, because we only know intelligent physical system. Whether they are ants, cats, people, whatever. So, and which characteristics should have these agents? Should be, it's for sure should exploit law of physics, and I've shown that in walking, we exploit the law of gravity, so it makes sense. Need to generate the sensory stimulation, and in fact, if you think to the baby, because the babies are the inspiration, no? Because before being an adult, listening to lectures, or attending lectures, you are a baby and try to catch balls. It seems that you first need to be able to catch balls, and decades later you are able to catch concepts. No? And notice, catch concept. So it seems that is embedded in our brain, the idea. Even when I'm talking about abstract entity like concept, I'm using metaphors that are deeply embedded in my brain. Yet another digression. There is a very nice book by George Lakoff, Where Mathematics Comes From. And this work has been completed by one of his students, who is R. Nunez, maybe Roberto Nunez, where they did initially an analysis of this kind. For example, when a calculus professor talks about the limits, say, when we go to infinite, what has been shown is that if you ask a mathematics professor to do the demonstration in a PET machine, the center of movement in the brain are activated. So he's actually going to infinite. So this is a digression. So when I say grasping the concept, I don't know. I don't have an online PET imaging of my brain, but it's very likely that even if I don't do this, I say grasping the concept, someone is moving and is part of a system which activates my grasping movement. So what is really, this book is really worth reading, because you think of abstract mathematics as something that has no link to your body experience. Actually, it seems that it is built on body experience. So it's a kind of, it's an abstraction, but your body use that. And so this idea of sensory stimulation is that, so why babies play a lot? Because they need to build relations between the movement and you must be able to affect environment. So why you realize that you are awake and not dreaming? Because if I launch this and stay here, it will follow my head, and I will have a sensory stimulation. So I know that this exists. and then complex dynamical system, because they cannot be nowhere, and perform this morphological computation. And then so this everything about emergence. In nature, large number of parallel loosely coupled, like molecules in the cell, asynchronous, and this is for us is strange. And I insist on this is the coupling of the agent with the environment. This led, for example, you may have heard about the very early work of Rodney Brooks, later on the founder of Roomba, and now great guru of robotics and the AI community. Was the founder of Exile at MIT, the AI lab at MIT. In the 80s, he came out with this, raising this point, saying, okay, the classical model, cognitivistic computing approach, is that I have sensor, I have actuators, and then I have a perception system, which tells me where I am, what I want to do. A modeling of the world, a planning system, and then I act. So I send electricity to the motor. He said, well, I think that looking at nature, we should implement a different architecture. But by the way, it's still the architecture that 20 years later had been implemented in the Roomba vacuum cleaner. So I have a set of concurrent parallel behaviors which do different things. For example, one tell the robot to move randomly, explore. The other manage getting object when you bump into an object. And the other is to go back when you hit a wall. So this is, if you have seen a Roomba or a movie of a Roomba, is exactly what it does. So the idea is that I don't have a single brain. I have a collection of different concurrent behaviors. So concurrent means that are behaviors that execute continuously in parallel without being coordinated. This is the famous subsumption architecture, and it was in a famous paper by Rodney Brooks in 1984, I think, 4 or 6, and it was intelligence without representation. And that was, and of course, this kind of reasoning that I was doing, and it was based on this Genghis robot, which was implemented. So this is the grandfather of Roomba. Interesting, years later, this German biologist studied how ants walk. How ants walk, okay, you would expect, but now you know that it's easy to know, but it's not so, that there is a kind of syntax. So the brain of the ant is used to walk. No, it's used to decide the general direction. The walking is coordinated by a mechanism which is not in detail, no, but is the coordination between two close legs. So actually, what Olk Cruz has shown is that the ant is programmed with a subsumption architecture. So you can cut the, actually this is an example that some Nazi biologists did in the 30s. You can put a cat on the treadmill. So I quote because it's scary, but it's interesting. And it works on the treadmill, the cat. If you cut the head of the cat, something that now you won't be allowed to do, the cat works on the treadmill, exactly like when the cat do the same experiment inhibiting the communication without cutting the head. But in those times, the only way to do this. And so this idea of having the coordination of the legs at the level of the legs has been inherited by cats and maybe also by us. So nobody put someone suspended on the train without head to see how it works. But it's likely that the result would be the same. So, and the principle is this one. Then it was noticed, because there are really very things to tell about this. Another interesting question is this, no? Because already in the 90s, this Kirsch, which was, I was talking to you about paradigm clashes, and the reason why I did that, the long introduction of methodology and possibility to compare is that it risks to become a religious fight. And this Kirsch told, which was on the other side, told, yes, but what you mean is that I understand you are able to explain how ants are able to behave properly. Are you saying that this same mechanism scale up to allow complex philosophical thinking or having sophisticated sentiments? And actually, Rodney Brooks said, well, you see, okay, there are publication times, but I had to think for some time. And a few years later, yes. So you can, I suggest if you look, you can find easily on the internet, because that was a long discussion, but finished with, okay, we will see. And why finish it with, okay, we will see? Because we at the time, and they have then the tools to check if this was real. But it's very interesting because I mean, because it's a long way. No? For example, this Lakoff, which did this study on the brain of the mathematicians, was trying to show that Brooks was right. And it seems that Lakoff hadn't the tools, but Nunez later, that is now, I think, at Stanford, was able to show that if I ask a theoretical mathematician to demonstrate a theorem, he will move. This is the limit. Maybe okay. I told you we could spend really weeks on this, no? Because you may say, okay, you checked the limit, but maybe other concepts are not linked to motion primitives. Because the thesis of what the mathematics come from is it comes from motion primitives. It's a cultural construction of motion primitives. And that's why it's useful when I show you the work in this way is more effective than telling you stay in this way, because when I move in this way and I mimic the fall, your brain connect and you activate and this give it to you the impression of having understood better. And maybe it's so. So you understand better because you empathize, so you mimic the dynamics. The experiment of a cat was done also with a robot. And this robot was built by Fumiya Ida, that then was in Zurich, now is in Cambridge. And this example, well, he built. He couldn't build a cat, because you understand, when we talk about mimicking animals, we have a small problem that for us, building a multicellular system like a real animal is extremely difficult, so we are not able to do that now. Notice my now. So he had to do some compromise, but the compromise was very, so he built this, unfortunately it's not so clear the picture, but what he put is, he built a very simple structure, putting springs between ear and ear, a number of springs with no motors, absolutely no motors. So it was like the cat without head. It put it on the treadmill, and it was able to gallop very well, things that those robots are not able to gallop. This was systematized in a famous for me, so famous for actually it's another article like that by Brooks. This article in Science in 2007 by mainly Rolf Pfeiffer, but one of the other authors was Fumiya Ida, who did the experiment. So in practice, you may imagine, Fumiya was the student of Pfeiffer. Pfeiffer had the ideas, and Fumiya put the things, did the hard work. So this model of control. So the idea is that the information self-structure, the environment has a critical role because whenever that system, that snakebot, uses a very abstract concept because measuring the predictive information on the expected sensor values after actuation is very abstract. But it's abstract, but it fits with any terrain. And so the terrain is part of a control loop. Another important part is in the case of a cat with this puppy made of iron and springs, is the mechanical strata, and the controller is emergent. In the case of a cat on the treadmill, not the cat, the puppy, so the robot, this simple robot on the treadmill, there is no control in the zero implementation. So you put it on the treadmill and it gallops. And you understand that you move by the treadmill, you give energy. No? But basically, it means that it is the structure, which is a dog-like structure, which by itself is able to perform. And then one more step. More or less in the same time, Lucarella and Sporns, that I don't remember where is the Sporns now, but Sporns is actually a person who did a lot. If you check Olaf Sporns, you will find many interesting things. Actually, he's trying to develop an information theoretic model of the brain functions. And he's probably one of the people doing more work in that area. The experiment that they did was this one. They took 3 different robot settings. So a spider, a mobile robot in a simulated environment, and a very simple humanoid, which has to move that orange ball. And then they put a training system based on a slightly different flavor, maximization of the transfer entropy. And what they noticed is that when you look at the behavior, and it seems fit to you, so the robot is able to grasp the orange ball. The other robot moves properly in the maze. And the spider do the same in the real world. Always happen the same thing, the transfer entropy or information flow, which is kind of predicted. So it's, okay, I may have, I don't know if I have slides about this, but so it's a matrix built on Shannon entropy that I will show you in a minute. So this strange communication matrix, transfer entropy is maximized, but when it works. So the suggestion is, okay, so it makes sense. So this is a kind of back explanation of snakebot experiment because snakebot was in forward. So I think that maximization of predictive information can be the driver of the evolution of the good behavior, and it works. Here is the opposite. So I train without any idea a simple generic neural network to grasp this orange ball, to go to point A to point B with a spider, and to go to point A to point B in a simulated world with a mobile wheeled robot. In all these cases, what is maximized is that. So I may simply use that as a driver. Another example, cluttered. No, I was talking about the fact not all the rooms are not the same. So this is to explain why this entropy measure are interesting in this context, because how I can say that a maze is more messy than another one? For example, it was proposed to use the entropy of a grid. And what is nice is that if you define this entropy, which is, again, it's the entropy, Shannon entropy, for those who knows it, but it is calculated on the grid. So I look, black or white is the value that I put in the eye. And it shows to be a nice matrix because it becomes higher when the environment is more messy. So the problem is developing a system which is able to manage as much information depending on the environment. Because when I say that it's even difficult to measure performances in robotics, is that a robot which goes from A to B, in the first case, so 0 complexity on the maze, okay, it's good. One which is able to move from here, so to go here, from here to here is better. But I need a matrix to say what is cumbersome and what is not cumbersome. And also, going back, it would be interesting to see how the dream is. I measure this, which is at least is a proxy of the complexity of a task. I measure the transfer information of a controller, and then I check which part of this information is stored in the dynamics and which part is stored in the program. So giving, and this is, it's easier to be done here than but the idea is that, so in this way I have the complexity of the environment and the task, and I have the, so okay, I will probably give him the, so we have many people working on this. I quoted already Tanev, that was the inventor of the snakebot. Propocampo did similar things. And then there are details that I will tell you where you can find. For example, there are subtle differences because, for example, there and others have used a matrix that is called the time loop error, which is how you, in a basically, it's not the same. For a Gaussian process, it's the same. For general process, it's not exactly the same, but the time loop error is, I have an algorithm which projects the position from x at this moment to x plus tau. And then I measure where it is, my system is at x plus tau. This difference is the time loop. So no, the difference that then from this point I use the inverse of the algorithm and I measure from where it was starting. And the sum of these two errors is the time loop error. So it's a measure of quality of the capability of prediction of the algorithm. I will give you some. Unfortunately, if I give you all the details, we will never go away from here. But I just want to give you an idea of the approach. Then there are different other approaches, but the two main approaches are elaboration on the mutual information, so the mutual information in time, so the information at point x and point x plus tau. And the other main approach is this time loop approach, which is, as you can imagine, is another measure of how good is the algorithm to predict, in this case, the algorithm managing the behavior to predict the future. Then there are And this is one source. So one source of information is Shannon entropy, so information theory. And meaning as a theory of communication, right? The other source is network science, because if I want to emerge from a system of many agents, the place where I can look for models is network science. Then, although it may seem very strange, until very recently, nobody thought of, very recently, in comparison to how old is theory, control theory, until this paper by Touchette and Lloyd in 2004, nobody thought to look at a control loop as a communication channel. Which kind of communication channel? Because I have the vector, the x is a stochastic variable. So I have a value of my stochastic variable, which will be a vector giving me the state of my system and the world. And another stochastic variable, which gives me the future state, next step of elaboration. And then I have this stochastic variable feeds the sensor, and there is a stochastic relation because you look, so the sensors are not perfect. And if you focus on a biological kind of systems are not at all perfect. Then the sensor is used to feed the actuators, and then the effect of the actuator and the effect of dynamics of a system will lead to the new state of a system. This can be simplified, so I can, for practical reason, to say that, okay, assume that when I have sensed from the sensor to actuator, there is a deterministic system inside. So it's the same considering this or this, and I call it C, the controller. And then the other part is a little, this is a feed, is the model of a feed-forward control, so with no feedback. So actually, the state of a variable is only due to some stochastic relation with the original value and what I do with the controller. And this is a way to, this is a trick because actually this can be decomposed. So this is not so, the important things are that this can be simplified to into this because when I am inside the controller, the system can be assumed deterministic. So it's a matter of choice. So there is a direct function that allows me to calculate A when I know S. So I say that I have C, and I don't care. And that is not a feedback, but is a feed forward. And this is a trick to say, OK, I can decompose the action. And this is more interesting if you go into the paper because it's the trick that it is used to develop the what? A controllability, what you do with control systems. So criteria to say that if your system is controllable, if your system is stable, and if your system is observable. So to my knowledge, Touchette and Lloyd were the first to do this kind of exercise from, because then, sorry, because this is first, maybe the only interesting slide. Because the channel, all those arcs are communication channels that I manage with according to Shannon criteria that I can. So moving from there, it was possible already. This is an article actually by me, 2007, I think, at least the first in 2007 and the other 2008. It's possible to do what? Something that was already tried with a different approach by a Russian in the 60s, and Anton Brudno, which actually wrote a paper on entropy and the complexity of mechanical trajectories. And he used an approach where basically he took the trajectories and he put them in small boxes. So it's similar to what we have seen from the maze. You remember the grid to save the complexity of a maze. He observed that, okay, my trajectory is something that moves in the 3D space, and some trajectories are straight, so I can put in one box. Some trajectories are more messy, and so I can put in many small boxes. The entropy, depending on how many boxes I need to describe the trajectory in these boxes languages, means that the trajectory is more complex. This work, I think, was almost unknown. So it was published in Moscow at the conference in the 80s, but was mostly unnoticed because many times the mathematical problems need so it's the nice thing about mathematics, I think, that mathematicians develop ideas that they seem not have any practical usage. But then, decades later, someone say, this was exactly what I was looking for, because you have the problem that mathematics solve. For this Professor Brudno, the problem was how to classify trajectories in terms of complexity, which is not trivial. So, and so it's possible to derive, for example, the very first of these relations links the complexity of a trajectory to the compression in the state space. So this explains why, if you have a limit cycle, you need less complexity in the program. So in the next I will show, but this requires really to. And then this can be generalized by using the rules of how information is transferred in the networks to a multi-agent system. So the entropy of multi-agent system, and it is actually bounded by, because you may have, because the problem, I have a big system which is made by many subsystems which do something. And here the idea is that, okay, exploit the dynamics, because if you can characterize how much you have compressed the available state space, because if I have a pendulum, the pendulum is not a moving particle. No? If you have a mass, a free mass, the free mass can go everywhere, so as a huge potential state space. If I link the mass to a wire, to a point, so I link to a point, so I create a pendulum, it cannot go in many places. So I have compacted and the nice thing about the relation one, it shows that it's true. So if I compress this, the complexity of a program has to be less. And that all those relations has been derived by the criteria of controllability that you can find in the Touchet and Lloyd paper. And this is a generalization. This is what happens if I have many parts. How having many parts contribute to the final results that I find there. And then, the complexity of what I can control in terms of a single part. People is flying away. And finally, the same relation can be linked to the first one. So this is, and now, before everybody really fly away, another hidden complication is that in a physical structure, you cannot do everything. So in a physical structure, you have only certain possible mobility, and this is can be modeled by the transformation group, in particularly groups. So here we have the demonstrations. And here the demonstration for the multi-agent systems. And here, really, since we don't have any more time, so I mean, I think that the main point is that information metrics and the concept of information-driven organization can be used to model the kind of phenomena that we see in nature, and also can be used to design systems with similar characteristics. And here is already we see some application, because, for example, Polanyi and others, and Naive and others at Hertfordshire University in the UK, developed a method to build artificial eyes. You know, the insect eyes are composed. The idea is by which criteria these different small eyes are put together. By using evolutionary algorithm, they were able to show that you can obtain eye structures that are very similar to the natural one, assuming that your eyes interact with a sufficiently complex world. What I did in that artificial life article, so basically they train the eyes on different images until they get a specific shape. And what they got was this. So depending on the train set of the images, you have different shapes of the eyes. But all those shapes are kind of similar to the real eyes. What I did in this artificial life article, what I proposed was to do the same game to evolve behaviors. And so this led to some further complication, because you need to calculate the entropy in a different way. But it's matrix multiplication, so it's not something that you cannot do. The fact of so because in continuous, this is the entropy of a kinematic chain in terms of Lie group. So these G are the coordinates in the Lie group representation. So it's different. It's more complicated. And the way to calculate it is making some integral. Why these Lie groups? Because the problem with this, this I will really go far. The problem that you have with this information-driven metrics is that to calculate, for example, the mutual information between two sensors, you need to sample many states. And if I don't know, if I need to sample the whole space of the whole possible value of a variable, it's computationally heavy. But if I have a structure like this, that it is not a real serial kinematic chain, but it's very similar to a multi-body rigid kinematic chain, I can use as a model the Lie representation of the movement. At this point, this formula, which seems terrible, this thing that seems terrible, it's the price, this formula that I pay to avoid to sample hundreds of time values on a big vector. So it's nice to understand if you do something like that. And this could be another nice topic, because Tamar Flash at Weizmann Institute in Israel has shown clearly that when we plan movement, we don't act in an Euclidean space. And a Lie group space is not Euclidean. So there are shortcuts to avoid to do all the calculation. Why the Lie groups? or something like that, or some non-Riemannian geometry, because calculating these metrics just by collecting the data is heavy in terms of computation, so cannot be that. And then this, just as a reading suggestion, this book by Chaiting, that was actually one of the people working on algorithmic complexity, he was suggesting that life is a random walk in a program space. And my point is in a random space of embodied programs, because living systems are not programs. Anyway, if you look at this book, you will see that it basically proposes an algorithmic model of life that could require another hour, and so I skip. But the idea is that I agree with Chaiting, but the random walk is in a physically embodied programming space, where a physical program is the control of this hip plus the physics of this leg, which is slightly different. So slightly is substantially different. So this is our current humanoids built on the good old facial paradigm. These are passive walkers. Now I just so this is no? This is a standard humanoid going down a ramp. This is deterministic. You look at the behavior. It's nice. I like with music because you feel a bit empathetic with the robot, because it doesn't fall, because this could be one of 200 movies. You see, because it has to calculate everything, and why it's difficult? Because if my working model is estimating my future center of mass and planning the movement of a leg accordingly, I needed to do many calculations. And you see, it's really, it seems me working on ice. So it's, you see, then in this way, recover a position, and then in contrast, you can see this. No programming, no nothing. It goes down. This is a historical, we skip the, and this is another thing. This is about energy. Now, okay, these are a lot of people. Now will appear the robot. This robot, with a single battery, was able to work in this stadium for 60-something kilometers. And this is the record in the endurance for a robot. This robot did 64 kilometers walking on a single battery charge. The critical observer will know that all this is very nice, but okay, this will be for another time. But it's very simple. So the humanoid robot can also say hello. The now robot can also grasp an object. This robot can do 60 kilometers, but nothing else, and with a constant speed. So I will skip all this very interesting part on other example of application, because this state approach that we have used to the control of an underwater classical arm, and later on to this stuff. So we are able to control this stuff, and we don't know even how it is really built, with a belief space planning approach. What has in common the belief planning approach and why we are interested with, which is a bit more ground level, but is inspired. So it's again a stochastic approach, because the problem is if you don't know the structure, only stochastic approach will be here. Then the next natural stage, and now I will really try to finish, is going beyond this and apply it to some interesting problem. Because the problem with now very popular machine learning and deep learning approach is that they don't have a concept of mass. And this could be linked to the reason why if you don't exploit Lie groups, you needed to take many samples, and so the system becomes computationally and data really heavy. The idea is that by exploiting something like that, you can have extremely less data hungry with H, data hungry learning system. Actually, there is this ongoing cost action where a group of people coming from gravitational waves detection, robotics, and geophysics are trying to adapt develop a learning system for physical system. Conclusion. So this is just two slides. So what if you are active in robotics? What you should do? You should exploit the many things that can be done with current paradigm technology. Maybe exploit something from here. Work on the models, and you have seen that it's not easy at all. And work on the experimental methods, because if you don't have performance evaluation is a driver or what you have to do. And this is not mine, it's from my colleague Bongard from Vermont. It's a nice explanation why he's interested in this discussion. Because this is, if you wish, non-embodied AI, is embodied in the computer. So it can play Go, it can play chess. It is quite good and reasonably good in computer vision, not perfect, not as good as in Go. It's almost good in natural language. So I take this technology and I move to robotics. So for example, the kind of experiments that DeepMind and Google are doing in manipulation robotics are taking this, typically the deep AlphaGo or AlphaZero, and take them on a battery of robots. Because if I need all those data, I need 100 robots, and this is a real room where they are training robots, to train the algorithms. And this means that I add one dimension, and this dimension is the embodiment, so the physical structure. But in these robots, the physical structure is fixed. In the kind of robot that I was pushing, the physical structure can change. This means that I have much more possible behaviors that I can implement by changing the physical structure. And now we come back to this seemingly abstract discussion of morphological computation. Why? Because we started from the pendulum that everybody knows. The model of that corner ranger that we have seen to be so effective can be that inverted pendulum. There is a paper, the simplest walking model, that you can check, where one of the authors is Ruina, where you find that. But what you find is that the period, which is linked to, so the gate period, the speed, is linked by a function to the length, to g, okay, and the length of the legs. So no possibility to change speed. But we change speed. Why? Because we are deformable. So the task how to control a robot like this to do the things that now is able to do is being able to change the structure. So soft robotics, that seems, you know, in academia you invent new topics because you need to publish, right? No, it's an essential point because if you want to exploit passivity, you need compliance. And this is shown clearly because if you don't want fixed speed, you need to change the structure. And so the simple way is, this was Asano some times ago, you put no, you understand also backward, now I know why I have a knee, because this can change the relative, so this pendulum can change the period depending on how I'm using the muscle. We do it not consciously, but we do it all the time. So this is the link between the two problems. And now I finish with references. So, there are these lectures that I've been coordinating from 2013 and were actually initially started by Rolf Pfeiffer and Josh Bongard. Rolf Pfeiffer now is retired in Malaga, I think. How the body shapes the way we think, but I think it's really an interesting book. The limit here is that this is a kind of Copernicus level. So here you have a list of the principles that probably we should implement. What you understand, it is now 10 years old, is that at least at that time there was no idea about the models. Because it's very compelling that the models are not, and these lectures are every year, are online and free. And they are, so if you check the website, you will find a lot of lectures on this kind of issues. And this is, so if you are curious about the references, there is this book that should likely come out where I edited by me and other colleagues, which is in the cognitive system monograph. For example, I hadn't time, unfortunately, sorry. Scribbling movement. So this Tamar Flash, Alain Berthaud, and other researchers who are neurophysiologists, and Tamar Flash is a mathematician, have studied how we plan the random scribbling. And we optimize, but we optimize in an affine geometry. So not, and this is, but if you think about why you should have Euclidean geometry in the brain, Euclidean geometry is a cultural invention of the Greeks of 2,000 years old. So we have probably some higher level structure that have inspired the Euclidean geometry, but is much more powerful. So probably what we are discovering now was already in the brain a lot of time before, because it is used to plan model. And so, spasiba, and thank you for your patience.
Thank you, Fabio, for your lecture, and maybe some questions. From my side, I have one, but
no, I will give you a short answer, I promise.
Two sentences, yeah. I get that you are proposing for the soft robotics to balance the rigid structure and the flexible structure and transfer some abilities to the dynamic of the system. But what approach, mathematical approach, will help us to find some optimal position, like entropy? Should we measure the entropy?
Yeah, actually, the proposal in that artificial life article was to use the information, so to maximize, for example, information flow, transfer entropy, In that book, there is a long chapter where everything is explained in detail with all the necessary formal clarity. Exploiting LIGO. So my idea is that you should use an evolutionary programming approach, any of them, on the basis to optimize, because evolution needs to optimize something, maximizing the information transfer, so the predictive information like in the snakebot, but considering the Lie group structure of the system that you may write by hand or you may identify. This could be a way to do things. Then, if you move to an article which is still to be published, if you move to, because I mean, we have soft parts, we have a very compliant and strange connection, but we also have bones. So we use, rigidity is useful. Now, because if I want to move this point from here to here, the quantity of information with a rigid body is much less. So it's enough with an angle. If it is deformable, I have much more variables. So the idea of why the morphological computation is important, because many things are not relevant. So the important thing is it moves. So the idea is to generalize this to a simplified finite element methods. So I've seen, for example, there is some work of people that try to really do a finite element methods model of a deformable structure and then control element by element. My point is that that's going to be very heavy. I should abstract a few things because, of course, it is deformable, but if it is a single body, it's connected. So the idea is that the FEM model could be similar in a really soft robot, could be similar to the snakebot in 3 dimensions with force applied. So it's a challenge. In fact, when I say that on the 3 axis, on this of the application, I'm very, very, very confident. On the experiments, I think that we need to improve the methodology, and it's a matter of social, so it's a community learning process. On this direction, we need breakthrough. So it's real research. So we need some ideas to go forward. I think this could be a starting point. But of course, you need to test. You need to, in many cases, I promised the short answer, and I couldn't. Okay.
Any questions more?
I have a question. I'm a chemist, and interested very much in the point of view of models of self-organized systems. And I didn't catch, honestly, from your point of view, where was chemistry. You show a bit with a cell, with molecular reaction. What you're talking about planning is nothing to do with molecules and chemical reactions. As far as I understand, it's just movement as usual soft robotics do, which we can just do with a silicon, pneumatic.
No, I didn't talk about that, but one of the points, because what I say is that you start from the easy problems. No? But for example, a problem where these concepts of, if you want, dual function of information processing and physics, in this case, physical chemistry, is a protein folder, for example, or the matching of antigens and receptors in lymphocyte is something on which we are also working. Because from when I said I did the example of a mechanical system because it's that more familiar, because almost everybody have seen the pendulum experiment in some phase of the education. So everybody knows more or less what it is. So mechanics is a, the system can be a chemical system. In fact, in that artificial life article, I also, a number of references are, for example, on artificial chemistries. So, structure that you can build on chemistry by constraining the condition of the reactions. No, chemistry is relevant. It's more difficult. And another thing is that, thank you for the question, because, for example, when we say that neural networks or deep neural networks are equivalent to what happens in the brain, we are not correct. A deep neural network is a long polynomial, is a kind of a long polynomial identifier. No? But what happens in the brain is that a lot of information, Shannon information, is transmitted by chemistry. And this could be one of the reasons why we have so much difficulties because now, there is a huge project, which is the Human Brain Project. Then there is the more Anglo-Saxon and humble brain mapping project in the US, but there is also the China Brain Project. So there are a lot of people trying to build, the idea is that I create a big simulator of a brain, doesn't matter if it is big like this building, and then I use it to have an intelligent behavior. So a copy, a big copy. But what probably not getting correct is that they are building a huge neural network. So a structure where I have a vector which, depending on the threshold here, change of value. In the brain, there is a lot of chemistry ongoing. So when I say system, I think any system, and in the case of biology, is clearly a chemical system. So when you study the protein folding, the protein is a long chain. If you look at kinematics and mechanics, is a long chain. It's like again the snake, but it's a chain of balls which are connected loosely, no? Because they can move one relative to the other. But then they can interact chemically. So to a certain, the model that I proposed needed to be integrated by the possibility of having a chemical reaction. And you know that the protein folding problem is open. So
do with energy? Because if you are just doing physical changes, you can calculate easily with the chemical changes and the change of structure or folding or defolding.
no, what do you mean? Sorry.
If it's in a water solution, it's a molecular dynamic. No one calculated ions and water molecules.
Nobody?
Calculated all together. I mean, they can calculate your folding of the protein, which is already big business. However, if you are talking about all ions and other interactions, you should take all of them into account. What is in a simplicity? You think it's just easy
No,
to
in fact,
simplify? Because I think your snake is far away what's happening with the protein. I apologize.
what do you mean?
Because nothing with the dynamic.
No, well, consider my standpoint. So, meaning that I'm starting from a completely different kind. So my comparison is the now robot. No? So it's kind of natural to think. No, what I think that of this kind of consideration can be, but I don't know to what extent has been done. I know some colleague in the US that done, and it's a guy called, it's an Armenian actually, it's Gregory Chirikian. He was at Johns Hopkins. He developed some model of protein folding where he worked on consideration like this. So because the fact that I think people working, but I'm just starting this thing. So I'm working a bit on these things, but I have nothing published, so I'm telling openly what. But usually, apart from this colleague in the US, people working on protein folding don't consider information consideration. While as you have a consideration like minimization of energy, you also have a minimal information path. So they consider, because if you think,
Non-linear chemistry, non-linear chemistry is some out of equilibrium states, and
exactly,
you are not going to equilibrium. You are cycling between
exactly, but no, but my
until you are not going to this jump to
exactly. But you see
life is
that,
non-equilibrium.
so this is highly speculative. I agree with you. This I agree with you. But if you think to a system where things move to think, okay, it's another simplification, but think to Brownian motion. It's more likely that something agitating randomly take a short, in terms of information need processing path, than a long path. Very similar, for very similar reason that a configuration change triggered by a lower energy is more likely than one triggered by, but this is, no, I think there is, because the point is that the general point is beware that you should consider information when you consider physical system processing, doing something that can be considered information processing. And be aware that part of the work will be done by the system dynamics, which will follow some laws that make the chemistry are different from what of kinematics. But this trade-off will exist. This is my point.
Short questions. You are talking information processing, and I'm very interested in these questions. However, you are saying any movement is information processing. How you calculate in this case information in a context of information?
Yes, no, in fact, I was giving excuses in advance to, because this would require 1 week, not, but no, this is the point. So I can give a number to the trajectory in terms of complexity of a trajectory.
You can or
I
you
can.
can't?
For example, this Brudno proposed a method, one of the methods that you can use to say this, this trajectory is more messy than this one. But then I may agree with you that depending on the physical system, it's not necessarily that the distance in terms of, so that this is better than this, depends. But yes, I can give a number to the complexity, and also to how messy is the folding. This is really speculative, but the idea, but to my knowledge, only a few people have tried, but people is to consider not only energy consideration, but also information consideration, because there is this trade-off. But this is highly speculative. Because when I say this is blue sky, I mean that I already have to, I have problems to change speed on a robot. Let's imagine to change a pathway in a cell. So it's a big, but you need to, the idea is that you need to start from a simple problem and then expand. But
I don't agree with you.
you don't, no, I don't pretend with.
Another approach of self-organization.
What do you mean?
You are saying we should go step by step. I think it's wrong. We should think about function. Like von Neumann, think how the cell divides. He doesn't think too much about complexity of the process, what happened, and he was worried about function.
Yeah, but
I mean, the main, I don't mind to have all this soft robotic field, but
no,
people
you
talk a
no.
lot about information in it. I don't understand how much information is in it. I want to understand how much information when we have a finger and it passes. Is it possible to calculate?
Yes. Usually the value of information relates with entropy of the system.
So entropy is a simple way to give a number to the fact that something was very like.
Some simulation and it's computation.
No, if you are taking the closed loop system or just make the state of the system like closed without any foreign energy, you can estimate the value of energy inside the system and it will be related with the information. But it depends
No,
on
but
what
what
kind
of
you want to describe, the trajectories, or you want to estimate the legal value of.
Probably we discuss this.
Yeah,
Mm.
yeah.
No, but what I would bet, and not necessarily we need to agree, is that this morphological computation mechanism exists also in the biological system and should be taken into consideration because it's an oversimplification. But when I look at the strain of a DNA, I see a list of symbols. Of course, it's not a list of symbols, but that list of symbols is actually used as information. The idea is that there is not only this information which is stored in the ACT, G, but also the other information which is stored in the chemistry. What I'm saying is that there is information in the chemistry. By the way, there is a book by Paul. There is a book which was published in January, end of January, where maybe more because it's not my direct field. My field is this kind of strange robotics. I look for inspiration in that area. I have a feeling that this kind of consideration could. In this book by Davis, I think he does. So he studied more this problem that I did, and again is pushing the idea that information is an aspect that you should consider also in biochemistry, in life modeling, not in chemistry itself. And for example, I think that things are Prigozhin are important because are like the limit cycle in the dynamics of working, but I don't pretend that you agree. It will be interesting to talk more with you, but if you have time, when you will have.
Okay, from my side,
To go over that.
the messaging by
Good.
maybe we'll find something really useful.
No, because actually we are working on a project where we are trying to apply this concept to protein recognition actually, and you know, it's research. So in the end, we will discover that you knew already in advance, and we lost our time. But if you don't try, you don't know. Okay, sorry. So it's a bit, you know, brick and mortar approach.
Yeah.
I try. If there is nothing, okay, there is nothing. Okay, thank you for.
again for your ideas.
No, but anyway,